All right, so the first thing I want you to do on your composition notebook is put your name on the inside cover and then flip to the very back. So the last thing I want you guys doing is trying to memorize stuff. So we're going to use the back as a reference. We're going to put important information back there that we need all the time so that when you need it, you know where to go. So the very last page at the back of the book, title it Handy Conversions. And we're actually going to put 2 in there today. So the very last page is titled Handy Conversions. And if you don't have your notebook, it's okay. This PowerPoint presentation is online. You can skip back to it or look at somebody else's book and get caught up pretty quickly. So the last page, we're going to keep Handy Conversions. The second last page, we're going to put useful math formulas. So turn back a page. So the last page is Handy Conversions. The second last page is useful math formulas. So things like the area of a circle. You know the area of a circle? Pi r squared. In the heat of a test, will you remember that? Maybe not. So if you have it in the reference place, you won't get confused. So things we use a lot, we'll put there. The third last page, we're going to put math models for data. So our whole process of looking for patterns in data, analyzing our data, some things that will help us, we're going to put back there that we use a lot. Okay? And I'll tell you, when we're covering something, I'll be like, okay, put this back in there, okay? This is just to keep it organized. And then the next last page, so flip back a page, one more. And this is going to be our Unit 1 toolbox. So we're in Unit 1 right now. We're studying what is called kinematics. We're trying to describe the motion of objects. And when we get some formulas, we're going to put them there so you don't have to memorize them. Okay? So the back 4 pages, and then as we keep going, we'll have Unit 2 toolbox and Unit 3 toolbox. And then when we're in Unit 3 and you need a formula from Unit 1, you know exactly where to go to get it. Okay? And you can use your toolbox on all the tests and quizzes. Never memorize anything. Memorization is an 18th century skill. We don't do it anymore. All right, everybody good? Okay, so turn to the front of the book. You can write Unit 1, kinematics, if you want. We'll take a couple of notes today, and then we're going to solve some problems. Okay? So this is Unit 1. It's called kinematics. The study of motion. So yesterday we went out, we dropped wads of paper on the football field, we made a graph, right? We're going to study figure out what we can learn from that. All right, so first of all, don't write this down. I just want to explain some words I'm going to use. Distance is how far I go, right? Displacement is very, very similar. If I start here and I walk 10 meters, how far have I walked? 10 meters. My distance is 10 meters. My displacement is 10 meters. They're the same thing, right? Here's the difference, though. What if I walk 4 meters this way? What's the distance I've walked? 14 feet. Just the second one. What's the distance I've walked right there? 4 meters. What's my displacement right there? We're going to call it negative 4. Okay? So when you ask, what distance have you gone? You're just measuring how far you went. If we say, what is your displacement? We care about the direction too. Okay? So I'm going to use the displacement all the time. It's almost the same as distance. It just means we care about the direction also. All right? Does that make sense? So when you hear displacement, think distance. All right? So it's the same kind of thing. All right, so here's what we did in lab. This is somebody, Elise, of yours. So here's Elise walking along, dropping paper wads. She plots it. She gets a pretty straight line, and she gets 0.86. So when you graph distance versus time, what we are interested in is understanding the meaning of this. What is 0.86? the distance she walked every second. We call that the rate of change, or the speed. How fast she's going, right? When she's speed walking, she's going 2 yards per second. Significantly better than 0.8 yards per second, right? So this leads us to our first big idea. And so from lab, we can see the slope of the distance versus time graph is the rate that your position is changing. It is, in other words, the velocity. Okay? Now, just a quick reminder. Velocity and that thing's recording back there, so. Velocity and speed are almost the same. Small difference. If you're driving 60 miles an hour north, what does your speedometer read? 60. If you're driving 60 miles an hour south, what does your speedometer read?
60 miles.
Reads 60. Speed is just how fast you're going. Velocity is almost the exact same thing, except we're going to include the direction. Okay? So if I'm going to the right, I'm going to say my velocity is positive. If I'm going to the left, my velocity is negative. A speedometer doesn't tell you which way you're going, right? Speed is just how fast you're going. Velocity means the direction is included. And for our world, we're just going to go left or right. Okay, we're not going to go like 30 degrees south of west or anything like that. All right, so here's the big idea that we're going to jot down. Okay, so here's kind of how you can do it if you want. You can put all that in your book, or you can just do this. When we make a graph of displacement, and time, whatever it looks like, it doesn't matter what it looks like, the slope of that graph is the velocity of the object. That's the big idea for the first unit, believe it or not. When we graph displacement versus time, the slope is the velocity. Does that kind of make sense from what we've done? The slope is how fast you're moving. So you can write it down in words, or you can just draw yourself a picture. The idea, though, is that if you graph displacement versus time, the slope is the velocity. All right, so if this is the graph of an object in motion, what does it mean? So, any volunteers? What's your name? Trenton, sorry, Trenton. Trenton, think of a story involving a furry mammal whose motion is described by this graph.
Furry mammal. Accelerating.
Whoa, which furry mammal?
You said a furry mammal.
Well, you gotta tell us what furry mammal you're working.
A giraffe.
All right, you got a giraffe. Giraffe's furry? Okay.
They accelerated 1 meter per second for 5 seconds.
Okay, so it's going 5 meters per wait. What'd you say?
It accelerated 1 meter per second for 5 seconds.
Okay, so it's going along at 1 meter per second for 5 seconds.
Then it leveled off, so it stayed the same speed. Go on.
Almost.
Oh wait, no.
Remember, the slope is the velocity, right?
Yeah.
What's
okay,
this
so
slope?
it stayed. It didn't move.
Right. Didn't move for 5 seconds, and then,
Then it went back.
yeah.
to where it started.
So what I don't want you to say is a giraffe climbed a hill, walked over the top of the hill, and slid down the other side. This has nothing to do with the hill, right? There's no hill here. This is an abstract idea. We're graphing displacement versus time. This is showing where the giraffe is at different times. And the slope is the velocity. So the giraffe is walking to the right, positive velocity. What's the slope here? 0, so it's not moving. And then the slope is negative, so the giraffe is moving to the left. Okay, you see that? Now we can get a little more information. What's the slope here? It's 1, right? We go up 5 and over 5, the slope's 1. So the giraffe is going 1 meter per second this way. It stops for 5 seconds. Now what's the slope here? It's -2. So the giraffe hustles back, right? So, maybe we want to try a furry animal story? Why did the giraffe go to the right? Why did it stop? What made it hustle back? Come on. Nobody got anything?
Lion coming.
Who's that? What? Go ahead, Hunter.
There's a lion coming.
No, start at the beginning.
So the giraffe starts walking to the right.
He's going to get water.
Why?
Because he's getting water.
Oh, okay, yeah.
And then
He's drinking water.
Yeah, for 5 seconds. And then he sees the lion coming, so he hustles back.
All right, there you go. Okay, so that's a good story. All right, who's feeling good about this? They got this. Katie? All right, Katie, here you go. Here's one for you. So Katie, here's a graph showing the position or the displacement of an object versus time. Give us a story involving a scaly reptile. Loudly.
A lizard
Okay, good so far. You got a scaly reptile at least.
runs to the right
Runs to the right.
and then turns around and goes back left. And then goes back right and then back left.
That's true. That's boring as heck, but it's true. Anybody got a why? Who would make the reptile do this? You can think about it. That's a good job, Katie. So, remember, guys, this has nothing to do with lizards climbing mountains, right? It has to do with representing motion. Don't worry, you'll get more chances. You get to write a little essay explaining a marsupial on the quiz. All right, let's keep moving. All right, so back in the old days, we told you distance equals rate times time. You guys remember that? That's all we're doing here, guys. So distance is on the y-axis, time is on the x-axis, and that's the slope. We're going to change the variables slightly, though, because we're actually going to make this more complicated when we look at acceleration. So eventually, the lizard's going to be speeding up, going faster and faster and faster. Or the ball is going to be falling and accelerating as it goes down. So we're going to change our variables a tiny bit, okay? So we're going to do this. Instead of distance, we're going to use displacement. And the symbol we're going to use for displacement looks like this. Has anybody seen that thing before? Where have you seen a delta before? Elise? Anybody else? Where? Fraternities, yes. How about in science? In chemistry? Yes! Delta T. You guys remember delta T in chemistry? So here's the idea. Don't write that down yet. Delta T means how much did the temperature change, right? We took T final minus T initial. We're using it the exact same way. Suppose that Katie's lizard is here at 3 meters, and it runs over here to 6 meters. Okay? So I would say that the initial position is 3, the final position is 6, and the distance it moved, its displacement, is going to be the final minus the initial, which is 6 minus 3, which is 3. So we're going to use delta x to represent how far something has moved, its displacement, okay? We're going to use v for velocity because it could be positive or negative, so we can't say speed. We got to say velocity. And t is the time. So this is going to be the equation that explains the relationship between how far something's moved, how fast it's moving, and how long it's moving. If it's in uniform motion. So uniform motion means the same speed. If something is changing speed, you can't use this equation. All right? We'll get another equation for that. So this is the first equation we're going to put in our toolbox. So flip to the back, Unit 1 toolbox, write this equation, and if you want to, next to it, put when speed is constant, just so you know when to use it. We're using this when the speed is constant. And if you want to annotate it, you can. So we're going to put this in our toolbox, back in your book, so anytime you need it, you got it. All right. Give me a wave when you know a minute. Okay? There's some waivers out there. By the way, guys, all my PowerPoint presentations are linked on Canvas. Today it said Wednesday, and it said Uniform Motion Lecture and Conversion Review, and below it said Link to Presentation. Okay, if you click on that, you get this. You can always go back. All right, here's a problem-solving hint. Pay attention to units. Whatever units the velocity is in are the units you've got to use for the problem. If the velocity is in miles per hour, then displacement's going to have to be in miles, and time's going to have to be in hours. Does that make sense? If you don't pay attention to that, you'll be using the time in minutes and getting the answer wrong over and over and over again. Okay? So we got to pay attention to units. So let me solve an example problem. So this is the kind of problem we're going to solve today. Okay? I've got a sprinter. They run 420 meters in 1 minute. What is the velocity of this sprinter? Okay? This is a really fast sprinter. That's all the way around the track and a tiny bit more. So, first thing I'm going to do is I'm going to draw a diagram. So here's my sprinter. I don't know. How do you draw a sprinter? There we go. That doesn't matter. It's a physics sprinter. Here's the important part. When we're solving problems, we're going to have three variables. Delta x, v, and t. It helps to write down what variables you're looking at, so when you read the word problem, you can figure out what numbers go where. You may not know what 420 meters is supposed to be, but you know it's got to be one of those three. So it makes it easier to kind of figure out where it goes, right? So, what is 420 meters? Is it the displacement, the velocity, or the time? Gabby? It's the displacement. This is 420 meters. What else do we know there? Sam? We know we run 420 meters. What's this? It's the time, right? It's 1 minute. And I'm going to be really careful to write units on here, guys. It's 1 minute. I'll just put 1. And it says, what is her velocity in meters per second? So we want the velocity in meters per second. So, look at the velocity. Is our displacement in meters? We're good. Is our time in seconds?
No.
That's how you know you're going to get it wrong unless you make a change. So, we need a time in seconds.
60.
That's an easy one, right? All right. Now, this is overkill, I know. You can probably solve the problem with your calculator not doing anything else. But eventually we're gonna solve more complicated problems, so I kinda wanna model what we're gonna do. I'm gonna write my plan. I'm gonna solve delta x equals v times t for v. I'm telling you what I'm gonna do, right? That's called a plan. Here's my equation. I'm telling you what I'm doing with it. Now, how do you get this v by itself, algebraically? Divide both sides by t, and so the velocity will equal delta x divided by t. Plug in the numbers, that's 420 meters divided by 60 seconds. 42 over 6 is 7, so that's 7.0 meters per second. Sorry, Katie, you probably can't see that. Okay? I'm staying on this side because I got my video from like screen to there. Sorry. Okay, so there's a solution to a problem. How fast are they running? So when we solve these problems, I'm going to give you 2 of these 3. You just got to find the missing one. That's not so bad, right? Just make sure you keep track of units. Because a lot of times, you might have to do a conversion. Now, that was an easy one, right? What if they're slightly more complicated? Well, let's review conversions, because we're going to run into some of those. So, flip to the back where it says handy conversions. Unfortunately, most of the world uses meters as the unit of length. But we don't. So we're not familiar with it, right? I mean, if you're going 35 meters per second through New Pal, is that okay?
Yeah.
Well, let's find out. So we need to do some conversions. So, here are 2 facts that you need to write down because you don't want to memorize them. 1 mile is 4 loops around the track, or a little more than
It's a little less.
what?
It's a little less. A mile is 1608 meters.
1609.
Yeah.
Right. So 1 loop around the track is 400 meters. 4 loops is 1600 meters. So a mile is very close to 4 laps. Okay? But you don't want to have to memorize it, so just write it down. 1,609 meters is equal to 1 mile. So if you took 1,609 of these suckers and laid them end to end, it'd be a mile. It's close to a yard, actually. It's 1,760 yards a mile. The other thing that's helpful is that 1 mile is 5,280 feet. And there's no fun in that. Just write it down so you don't have to ever memorize it. So let me do 2 conversion problems as review. And I'm going to do them right here. Okay? Just review factor later. So, high school cross-country course is 5,000 meters. Even the high school cross-country course is metric. 5,000 meters. How far is that? So we're going to start with 5,000 meters. And we are going to multiply it by a conversion factor that gets rid of the meters and gives us miles. Do we know a relationship between meters and miles? Yeah, we just wrote it down, right? 1 mile is 1,609 meters. So the meters cancel, and we're left with miles. So grab your calculator, let's see if we can agree here. Take 5,000 divided by 1,609. You got it, Hunter? 3.1.
7752.
I'm going to go with 3.11. 3 significant figures is good enough. So a high school cross-country course is about 3.1 miles. Why is it 3.1 miles? 3.1 miles isn't a nice round number. It's because it's actually 5,000 meters. Junior high is 3,000 meters, and college is 10,000 meters. You gonna run cross-country in college? So, all right, so some of of you guys may have done it like this in chemistry. 5,000 meters, you may have done this thing. Does that look more familiar? It's the exact same thing, guys. You still would have put 1 mile, 1609 meters. You would have canceled your meters and you would have been left with 3.11 miles. You're just organizing it slightly differently. But what you're really doing is you're multiplying this number by 1. See, 1 mile and 1609 meters is the same thing, right? So the ratio is 1. So when you multiply it by 1, you change its value, its form, not its value. Okay? So I don't care which way you do it. I like the multiplication because that's more mathy and I'm a mathy kind of guy. But you can do it either way you want. Okay? Now let's do one that's slightly more complicated. That was a little easy. What if we're going 32 miles per hour? How fast is that in meters per second? Okay? 32 miles an hour. So we've got to get rid of the miles and get meters. How many meters in a mile? 1609. So the miles cancels the miles. If I stopped there, what would the units of my answer be? Andrew? Meters per hour. The miles canceled, right? If I stop there, I'd have meters per hour. Is that what I want? No. I want meters per second. So I've got to get rid of the hour. The hour is in the denominator, right? So I've got to get hour in the numerator, and I've got to get seconds in the denominator. Does anybody know how many seconds in an hour? How many hours in a second? 60 seconds in a minute. 60 minutes in an hour. So 60 times 60 is 3,600 seconds in 1 hour. If you don't think you'll remember that, put in your conversions. Right? 1 hour equals 3,600 seconds. Totally fine. 1 hour equals 3,600 seconds. If you think you remember that, don't put it in there. How many inches in a foot? Yeah, you probably don't need to write that one down, right? How many seconds in a minute? Probably don't need to write that one down. How many feet in a mile? Probably need that one, right? All right, so the hours cancel, denominator, numerator, and it leaves me with a meter in the numerator, and it leaves me with a second in the denominator. And so now I can plug in my numbers. Go ahead and plug them in and see what you get. Let's see if we can agree. Plug them in, show your partner, and if you both agree, we'll pick your answer. Except Debbie. Camden, you guys agree back there? You agree? 14 point what? 14.3 meters per second. You guys get that?
Yeah.
Okay. Does that make sense?
Yeah.
All right, so today we're going to solve some problems. We got about 35 minutes, so you should be able to get a good chunk of them done. The first couple are conversions. I want to see your conversion. The next couple are problems involving distance, rate, and time. And then the last ones are just looking at graphs and finding the slope, finding the velocity. Okay? I want you to work together, so don't try to do it alone. Talk to each other. If Katie has number 6 done and Elise is stuck and she comes and asks me for help on number 6, I'm going to tell her to go back and ask Katie. Okay? If you're both stuck, then I'll help you. So I want you to work together. I want you to talk to each other. Except for the 4 guys who are stuck on their own. Other partners. Sorry. All right, so go ahead and grab your computer. Find the link on Canvas to the problem set today. And you can solve this right in your notebook. Right after those couple notes we took. I'll leave this up here so you can look at it. So go ahead and get logged in, check your answers as you go, and then when you get stuck, holler, let me help you, okay? Don't go very long being stuck without getting help. I can't help you when you go home, so let me help you while you're here.